all my AP physics students, please make sure that you know each of these things. I'm not going to go through and read them because you can read them yourselves. All right, 2 ways to find the torque on an object. So the 2 that I was thinking of when I wrote this question are the torque is just r perpendicular to f. So if you have like the force and how far it is applied, you can multiply those to get the torque. You also can use the net torque equals I alpha equation. On your equation sheet, it's alpha equals net torque over I. Just multiply the I up and it looks like this, just like F net equals mass times acceleration, but torque, the rotational version. And then you also, I didn't think about this one, but then I did later, so you also can use a change in angular momentum over time. That will also get you your torque. That's just rearranging the delta L as torque times the amount of time. These are probably the most common ones though. If you increase the torque applied to an object, what would happen to the angular acceleration? Well, let's look at this equation right here. So net torque on an object. If it's the same object, then the I probably hasn't changed. So if I increase the torque applied to that object, then you're increasing the acceleration. So alpha would increase. You'd have a greater acceleration. The same way if you push an object and then you push with a bigger force, it accelerates more. This one, bigger torque, will angularly accelerate more. The rate that angular speed changes at. So it's tempting to just put omega here because it says angular speed, but I didn't ask what is the angular speed, or what do you call angular speed, I asked what do you call the rate that the speed changes it. How fast your speed is changing is acceleration, but how fast your angular speed is changing is angular acceleration. So angular acceleration. The change in angular momentum, so you could do the change in angular momentum is tau times the amount of time it's been applied. So if you have a big force for a long amount of time, then you have a big change in angular momentum. If you have a small torque, then that's not a big change in angular momentum. If you have big torque but you only apply it for a millisecond, that's not a big change in angular momentum. And then the other way I was thinking through is you can also do like the change in something is just final minus initial. And we know how to find angular momentum of something rotating. It's just I omega minus I omega, which is the final minus the initial. You can call it omega naught. And then you can leave it like this. You can factor out the I, assuming it is the same I, because if it's already rotating, your I isn't changing. Like this. So just actually subtracting the 2 final minus initial to get the change in angular momentum, or tau times change in time. Both of those would work. Number 1, we want to know if this is the rigid rod with its pivot point on the right end, so it's pivoting around this. So that's important to know what it's rotating around. So this is my axis of rotation right here. I want to know in which case does the bar have the greatest angular acceleration. So think about angular acceleration is net torque over the rotational inertia. These are all the same rod, right? It's just different forces acting on the same rod. So this is going to be the same, the I is going to be the same for all of them. So the greatest acceleration on the rod, or the rod with the greatest acceleration, is just the one that has the greatest net torque. Net torque meaning like the total torque acting on it. So if you look at D is just one force, so it only has one torque acting on it, so it would be like 2F, and then let's call the length of it L, it would be 2FL. C also has just one torque acting on it. It has the same force, 2F, but it's acted on L over 2. B has 2 torques, so I'm just going to add the 2 torques. Careful, you're not adding the 2 forces, right, because net torque is the total of the torques. So the first torque would be F times it's applied at the L, plus the other torque is this force, but it's applied at at the halfway point. I don't know it's exactly L over 2, but you get the rough idea. And then that would be 1 plus 1/4, so that would be like 5/4 FL. And then here I have 2 torques, so I'm going to add the 2 torques together. The first torque is F times it's applied at the length, plus the other F applied at L over 2. That's 1 plus 1/2, which is 3/2 L over 2. So I've got 2F L over 2, which is, I circled this, but that cancels out. It's just FL. This is 2FL. This is 5/4 FL. This is 3/2 FL. So then this is the greatest torque. Now you didn't actually have to go through and calculate each of these, because think about like multiple choice, right? We want to save time. You don't need to do all of this if you don't have to. You could have just said, okay, I want the one that has the biggest torque. So compare this one compared to this one. For sure, this one is bigger because it's the same force, but it's farther away. So this is going to be greater, so you can cross off C. And then these two compare to each other. Well, this is more forces at the same spot, so then you can cross off B because this one is greater than B. And then now we're just looking at these two. It's tempting to think that these might be the same because two forces, that's a total of 2F. But it's not forces we're adding together to find net torque. It's the, I don't know why I'm standing up here. It's the net torque. So these are not the same as if you just put two here, because this would have a greater L, a greater R lever arm. This one has a smaller, so this one ends up being the greatest because two forces at the biggest R distance is going to give us the greatest force, or greatest torque, sorry. Right, number 2, an asteroid moves to an elliptical orbit with the sun at one focus, as shown to the right. As the asteroid moves from point 2 to point 1, so let's say it's going around counterclockwise, that's just saying it's getting closer to the sun. What happens to the asteroid's angular momentum? So the angular momentum should stay the same because it is conserved. There's no external torque acting on the asteroid. External torque. And then for those of you like, how do you know there's no external torque? Well, let's think about the only force is the force of gravity between them. And we know that the force of gravity always points into the center. So if your force of gravity is pointing towards the sun, and then your distance to the sun is your R, see how your R and your force of gravity would always be perpendicular? So I just drew that for at point 1, but even right here, this is your R to the sun, and your force of gravity is that way as well. So there's no external torque. Your angular momentum is going to be conserved. And then the angular speed, well, let's think about, we just got closer to the sun, so it should be going faster in here. So your angular speed should be going faster. If you're talking about like the speed around, it's like speed relative to the center is what I mean by angular speed. You also could think about this as linear speed because it is changing position, but either way, it's going faster. And then your kinetic energy is, you can think about it as the 1/2 mv squared or the 1/2 I omega squared if you're talking about like the rotational inertia relative to the sun. Either way, you're getting faster. This might have decreased, but omega is squared, so it wins. So this is kinetic energy is going to increase because it is getting faster. And then we know that total energy is conserved. Total energy is conserved. So if your kinetic energy increases, that means that your potential energy must have decreased. Trust your conservation laws. Right, so this one is sketching a graph of the angular velocity as a function of time. Well, angular velocity is just omega, so we're going to look at omega as a function of time. Well, what is the angular speed at first? This was a typo, by the way, because it's obviously starting off counterclockwise, not clockwise. So it starts off, your omega naught is counterclockwise, which we said to take counterclockwise as positive. So I have a positive omega naught. And then if you look, I have two torques acting on the system. I have this 2 Newton, which would be going counterclockwise. And I have this 5 Newton, which is like going around like this, which would be clockwise. So let's make this negative and this one positive, because we said counterclockwise is positive, meaning clockwise has to be negative. Now, the acceleration comes from the net torque on the object, so if you have two torques, you just add them. In this case, because they're opposite signs, when I add, it's really like subtracting. So I still end up with a greater force in the clockwise direction. So my net torque is going to be going clockwise, because 5R is torque, right? We're not adding forces, we're adding torque, but it's the same R because it's the radius of the pulley. So 5R and 2R, but this is negative, would end up with negative 3R as your net torque. But you don't need to do the calculations, you just need to see that this torque wins. So your net torque is going to be going clockwise, which means that your acceleration, your angular acceleration will be going clockwise, both of which are negative. So I'm starting with a positive velocity and I have a negative acceleration, so start's positive, and then if your acceleration is the opposite way, you're going to be slowing down, and then you'll start speeding up in the opposite direction. Just like a regular velocity versus time graph if you had a positive initial velocity and negative acceleration. Alright, I am riding this merry-go-round, spinning around counterclockwise super fast. All of a sudden, a volleyball comes flying at me with velocity v, and I'm super athletic, so I catch it, and I want to know what happens to the angular momentum of me in the merry-go-round. Now, it's tempting to be like, ooh, angular momentum is conserved, and it definitely is within a system if there's no external torque. In this case, if I'm just talking about me and the merry-go-round, we do have an external torque. The volleyball is coming in, and when it hits me, it is definitely going, when I catch it, right, it's going to put a torque on me. It's going to push me back a little bit as I go around. So my angular momentum is going to decrease. And there's two ways you can explain this. You could talk about the volleyball exerts a torque in the opposite direction. That's probably one that is pretty intuitive. I think how I wrote it was, when I catch the ball, I'm going to then turn the ball around and make the ball start going this way. So I'm giving some of my positive angular momentum to the ball instead of keeping it for myself. That's, again, whatever way you want to understand it, both of those work, and it's basically the same idea, because you're talking about the total momentum is conserved, just not my momentum, because that's not including the volleyball's momentum when it comes into the system. Now, that brings us to part B, what happens to the angular momentum of me, the merry-go-round, and the volleyball. This includes everything in here. That's the entire system, so there's no external torque now, not fork. There's no external torque, so that means that it's going to stay the same. Momentum is going to be conserved. The volleyball's momentum is going to slow down, change direction probably, so it'll increase in the positive direction, and then me and the merry-go-round will slow down a little bit in the positive direction. It'll still add up to the same total as before, because technically this is like a positive angular momentum and this is a negative angular momentum. Oh yeah, that was going to make up the point. So yes, there is definitely a torque. The volleyball exerts a torque on me. It's going to push me back, and I'm going to start pushing it forward because we were both moving together. The same way when two objects collide like this, they exert a force on each other. But the point is that those torques are on one another, so it's internal to the system. It doesn't affect the total angular momentum of all of the system. Alright, number 5, a rod is initially at rest on a frictionless surface. It has a rotational inertia I. Puck of mass m comes towards the rod at some distance d, so we'll call this d, from the rod's pivot point, which is shown right here, comes at a speed of v0. When the puck collides with the rod, it rebounds at a speed of this, and what is the magnitude of the angular momentum of the rod after the collision? We're leaving it in terms of m, v0, and d, and we'll take counterclockwise as positive. So this right here is a clockwise motion. This one right here is counterclockwise. This is like a positive velocity. This is like a negative velocity. And direction absolutely matters for angular momentum, the same way this is very different than if they both go towards each other, etc. So direction definitely matters, so be careful with your signs here. And then if you were to write your conservation of angular momentum equation, you would say, okay, the momentum of the, a puck or something? Yeah, so the momentum of the puck before equals the momentum of the puck after, and the momentum of the rod after. We know that the puck is just mvr, because it's moving in a straight line, and then this is still moving in a straight line, mvr. This one would be I omega, but I'm not trying to find omega or I just want to know what this term right here is, because I just want the angular momentum of the rod. So then angular momentum of the rod is what I'm looking for. Now I need to plug in my values. This is m, negative v0. The r, over the distance to the pivot point, was just d. And then afterwards, it is m 1/2 v0 distance, like this. So then I'm going to, then plus the L rod, which is what my unknown is, I'm going to subtract this over. These are like terms because it's MV not D, MV not D, so it's just -1 minus the 1/2. Cross off. So negative, right, I'm going to put the negative up front so that doesn't confuse us. So -1 minus 1/2 gives us -3/2, or -1.5. MV naught D equals L of the rod. So then this is the angular momentum of the rod. It just wants to know the magnitude. So this negative sign just means that the rod is going in the clockwise direction, which is like the negative direction, which we already knew, but I just want the magnitude, so you can just say this is the magnitude. Another way you could have thought about it is, okay, the rod is at rest right now. So if the rod is at rest, then the change of angular momentum of the rod is just what the angular momentum of the rod afterwards is, right? If it starts from 0 and it goes to 5, then it changed by 5. That's the idea here. Where does the angular momentum of the rod come from? Well, it just comes from the change in the angular momentum of the ball, which is what we did. We took this one and subtracted them from each other to get the change in angular momentum of the puck, or I said ball here, but it's puck, whatever. And that's how you got the change in momentum of the rod, what the rod ends up with. Okay. Two people are sitting on a uniform seesaw with a fulcrum at the center of the seesaw. The boy is sitting on the left side, and the girl wants to know where she should sit in order to balance the seesaw. So she's saying, like, okay, how far away do I need to be in order to balance it? Well, we don't want forces to balance because we want no rotation, so we want the torques to be equal to each other. So the torque of the boy has to be equal to the torque of the girl. In order for it to be balanced, you want them to like be in opposite directions, which they already are. This one's going counterclockwise, this one's going clockwise. So they're already opposite directions. You just need to make their torques the same value so that they cross or cancel out. How do you find torque? It's RF. And then the force is just the weight, right? It's the force of gravity. So this is going to be the R for the boy times mg equals R for the girl times mg. And then let's assume they're different masses, because why would they have to be the exact same? So then you would say how far away the boy is times his mass, and we can cross off G because it's both of them, equals how far away the girl is times her mass. So in order to figure out how far away she needs to sit, she needs to know her mass, and she needs to know the boy's mass and how far away from the center, or the axis of rotation, which is in this case in the center of the radius. So you need the boy's mass, his distance to the fulcrum, and her own mass. Which is pretty intuitive, right? So if you were to like look at somebody and you're like, oh, they're much heavier, so I need to sit farther away, or they're much lighter, so I need to sit closer. So you are comparing their masses and the original distance to know if you should be closer or farther away. All right, number 7, a solid sphere of mass m and radius m has this rotational inertia. So this is the rotational inertia of the solid sphere. It's released from rest at a height of h on an inclined plane. So this is like this. It starts with some potential energy, and then it rolls without slipping. So it's rolling. That's not what it would look like, but that's okay. So it would have both types of kinetic energy, rotational and translational, at the bottom. And we want to know what the velocity, this is like the linear velocity of the solid sphere, is when it reaches the bottom. So we're going to write our conservation of energy equation. The gravitational potential goes to the translational kinetic and the rotational kinetic energy. This is 1/2 mv squared, this is 1/2 I omega squared, and this is mgh. Now, we are looking for this. H was a given, mass was a given, so I'll replace these with the capital M's. And then I, well, I can just substitute this in, so let me rewrite this. I is just the 2/5 mr squared. And then carry everything down. And then omega squared, but omega is not something that I know. But there was something important that was told me. It says that it rolls down the plane without slipping. And we know that if something is rolling without slipping, then the velocity that it's moving at is just the omega, the speed that it's rotating at, times the radius of the wheel, right? If you have a big wheel, big wheel, and it's rotating certain amounts times per second, then it's going to go a lot farther than like a small wheel that's rotating a certain amount of times per second. We came up with this relationship. I can put it off on the side. We came up with this relationship when we said that omega is like 2 pi over t, because that's how much like angle changes in a period of time. Your velocity is 2 pi r over t, because this is the distance you're going in a period of time. So then that's where we said, oh, okay, our velocity is just omega, but with a factor of r. So velocity is just omega, but times r. So then, if we can use our v equals r omega equation, we can just rearrange. Then omega is v over r, so when we have the omega right here, we'll just substitute the omega squared with v over r squared. So this is 1/2 I omega squared. The 1/2 is right here. I was 2/5 mr squared, and then omega is just v over r. And then I'm going to say that each of these gets squared, because then it's really easy to say, oh, this is r squared divided by r squared. That crosses off, because anytime you multiply something and divide by that something, it just cancels. 1/2 and 2/5, that's just 1/5. So, and then we also have an m in every single term, so I can cancel that out. So I have gh equals 1/2 v squared plus 1/5 v squared. 1/2 plus 1/5. Put it in your calculator, math, enter, enter. Or you can say, like, put it in terms of 10. That's 5 over 10 plus 2 over 10. So that's 7 over 10 v squared equals gh. Multiply the 10 up. So that crosses out. Divide the 7 over like this. And run out of room. 10 over 7 gh equals v squared. So then you take the square root, and that is your answer. 10/7 gh. Child is spinning on a merry-go-round, and they walk from the center to the outside edge, so they're going out farther, which means that they're spreading their mass farther away, which means they're increasing their rotational inertia. There's been no external torque, because he's just walking on the merry-go-round, so the angular momentum of the child in merry-go-round system is going to stay the same. So I can cross off these. So angular momentum of the system has to be constant. And if the rotational inertia increases and the L stays the same, that means the angular speed must decrease. So already we crossed off A. And then the reason your kinetic energy would decrease is because you have 1/2 I omega squared. This one is increasing and this one is decreasing, and they're increasing and decreasing by the same factor. So if you have like 5 times the I, you get 1/5 the omega, because they still have to multiply to the same L, but then the omega gets squared, so that 1/5 becomes like 1/25 and overpowers the same factor getting bigger. So overall would still get smaller, B. And these balancing ones, so it says that the fulcrum's at the center, meaning if there was no force, it would just be balanced like this. I want to know where I would have to position an upward force of F over 2 in order to keep the stick in equilibrium. Because right now I have a downward force of F. So think about, if I have a downward force of F, where would I need to put an upward force? You first should just think, like, does it go on this side or this side? Because if you have a meter stick and you have, this is the center, you have a force down, that's trying to go around counterclockwise. Yep, this is a counterclockwise torque. Because we don't really care about up-down, we care about clockwise, counterclockwise. Right now I have a counterclockwise torque, so I would need, I wrote CW, and that is definitely counterclockwise, CC. Counterclockwise, so I would need a clockwise torque to go the opposite way. If it's going up, which it tells me an upward force, so the place where an upward force would cause a clockwise rotation is on the left side. If you put an upward force right here, then it's going to start to rotate counterclockwise with the other one. That wouldn't balance. It has to be on the left side. So it must be on the left side of the fulcrum. So we can cross off all of these. I know it has to at least be on the left. If you're like, wait, what is she saying with the directions? Imagine your pen and it's rotating about the center. Right now you have a force right here. If you add a second force up on this side, that just makes it go faster. In order to cancel out, you would have to have an upward force, so like I need something to keep it in place. So if you have a force down, you would need another force up to keep it in place. So play with your pencil and see if that makes sense. And then now I need to know exactly where. I know it's on the left side. I just need to know like at what point. So this is a smaller force. I want them to have the exact same torque because I want them to balance. So I need this equal torques, right? If I have a smaller force, that means I need a bigger R. How many times smaller? This is half as much, so I would need twice the R. So half the force needs 2 times the R to cancel out. And then now we just look, what was my original R? Remember, R is the distance to the axis of rotation, so that would be this distance right here. This was my original R, so if I need twice that, you just double. At first it was 1, 2, 3 over, so I need to go another 3, or a total of 6. So this would be 2R on the correct side, and that would be point A as my answer. And then again, like some of this you can just think like intuitively. Oh, if I have like a heavier person, right, here's the bigger force. If I need a smaller person or a smaller force, you need to go farther away in order to balance that out. And the reason they're on the same side is this is pulling up and this one's pulling down. So here, this is counterclockwise and this would be clockwise, which cancels out. Now, if it had asked about a downward force, then downward on this side would be counterclockwise, so you need downward on the right side to be clockwise to cancel out. So the fact that I want a force pushing downwards means I need it to be on the right side of the fulcrum. And then now it's just thinking through exactly where based on how big the force is. This is 3 times the force. If you need 3 times the force, you have a bigger, or you have 3 times the force, you would need a smaller R in order to balance out a bigger force because we want to keep it the same torque as this original one so that they can cancel out to 0. Remember, we want equal torques if you're trying to balance. And then if it's 3 times the bigger force, then you need 1/3 the R because 1/3 R and 3F will just cancel out to have the same RF as before. All right, so then 1/3 of the original radius, this is my original, not radius, but original distance to the axis of rotation was like 3 unit things over. So I need to go 1 unit over because that would be 1/3. So then I need a downward force of 3F right here. That is what would cancel out. So at point H. Ms. Campbell places a mass on her spinning platform and applies a torque of 5 Newton meters for 0.5 seconds. She then stops. So at first, let's say it's something like this, going around counterclockwise, and then she stops it. She stops it and puts it closer to the center and applies the exact same torque for the exact same amount of time. How does the angular speed compare to the angular speed now compared to this angular speed before? Well, what we've changed is we've decreased the moment of inertia. So you've decreased I because the mass is closer to the axis of rotation. I'll just say to the axis. Now we want to know, okay, well, yes, we have decreased I. What has stayed the same? Well, normally we would be like, oh, momentum is conserved, but we're talking about a torque applied, so let's think through. What you'll notice is it's the same torque applied for the same amount of time. 5 for 0.5 seconds. This one also gets 0.5 Newton meters for 0.5 seconds. If we want to know the momentum of the platform afterwards, we can use our change in momentum is torque change in time. So the change in angular momentum of the platform in both systems is just the 5 times 0.5. So the change in momentum of both is just 2.5 units of angular momentum. And assuming they both started from rest, instead she stopped it and then reset it, so they both have this same angular momentum once they're spinning. So if they have the same momentum, so they have the same L, but the second one has a smaller I, that means that it must have a greater rotational or angular velocity, so it has a faster angular speed. Because I'm putting the same momentum into the system, but it's easier, right? The mass distribution is less, so it's easier to rotate something like this, so it'll end up going faster even though you're doing like the same torque for the same amount of time. You're changing the momentum by the same amount. What could she change in order to make this closer mass system spin at the same angular speed as before? So what we could do is we could, instead of applying the 5 Newton torque, you could apply a smaller torque. And there's 2 ways you can apply the smaller torque. You can either have a smaller force, right? That's probably the most obvious one. Or you could have the same force, but at a smaller R. Because remember, let's put this in parentheses, torque is RF, so if you want this to be smaller, you just have to decrease one of them. You could have a smaller force, you could have the same force, but do it at a smaller, so instead of pushing on the side, like push somewhere closer, but with the same force, that would have a smaller torque. Or, instead of applying a smaller torque, you could keep the exact same torque, but for less time. So let's say you still apply the 5 Newton torque, but now instead of applying it for 0.5 seconds, now you only apply it for 0.3 seconds, etc. That would decrease how much momentum it has after the torque because you're not putting the same amount into it. All right, and number 12, got a pulley that's rotating clockwise initially at omega naught. So here, this is going clockwise, which it says take counterclockwise is positive, so this we're going to call a negative. So when I draw the graph of my angular velocity, I need to start negative, and then I need to figure out which way my angular acceleration is. Well, you can tell the angular acceleration from the net torque. So this is the same as before. So this one is going counterclockwise, that's like a positive torque. This one is going clockwise, that's like a negative torque. And then they're at the same radius, so the bigger force wins. This is the bigger torque, so I have a negative net torque and negative acceleration. Really should have drawn this higher up because it just goes down from there. So this is saying it's moving in the negative direction and it's just going to keep accelerating in the negative direction. It's going to get faster and faster clockwise. Different things you could be given in order to find the angular acceleration. Try to think of it as many combinations as possible. So I just looked at my equation sheet and I'm looking for alpha. So I've got alpha in this one, right? And I'm going to call it, instead of theta and theta naught, let's just call that change in theta, move it over. So I could use the change in theta equals omega naught t plus 1/2 alpha t. And if you wanted t squared, if you wanted to use this equation, you would need the change in theta, so like how many times did it go around, because you could just say, oh, it went around 5 times. 5 times 2 pi is how many radians it went around, because each rotation is 2 pi radians. And you would also need omega naught, and you would also need the time. The next equation it's in is omega equals omega naught plus alpha t. For this one, you would need omega, omega naught, and time. So this being, remember, omega is like the final angular velocity. Omega naught is the starting angular velocity. And then, what else is on our equation sheet? The torque, net torque over I. Angular acceleration equals net torque over I. So you would need the rotational inertia, and you would need the net torque. And think about net torque. Let's say it didn't give us net torque, but it gave us RF, right? You can find net torque from there and then use that. Is there anything else? Let me see. I think I had one more. Oh yeah, there's that third equation. So remember, on kinematic equations, we have, that's a big glare. We have these 3 equations. And all 3 of these are like totally valid for rotational motion, but it only shows the first 2, right? This is the omega equals omega naught plus alpha t, and the theta is theta naught plus omega t plus 1/2 alpha t. This one also works. You could possibly need to use something like this, which would become omega squared equals omega naught squared plus 2 alpha change in theta. Instead of theta minus theta naught, you could just call that change in theta. And if you were going to use this one, you would need omega, omega naught, and the angle measure that it, or the number of like radians that it goes through in that time. Okay, number 14, disc and hoop are both released from rest at the top of the ramp, and they're going to roll down the ramp without slipping. That's like the V is R omega. So there's a relationship between the linear velocity or the translational velocity and the angular velocity of the thing. So however fast it's rotating also tells us how fast the like center of mass or like the actual object itself is moving down. So let's think the one that reaches the ramp or the bottom first is going to be the one that's going faster, right? So it has more translational energy and less rotational energy. That's K, rotational. Now rotational energy is the 1/2 I omega squared, and I know that the omega has some dependence on V, right, because this is determined by the omega, so the one that has less rotational is going to be the one that has less less rotational inertia. So then now it's just thinking through, okay, I have a disc and I have a hoop, and I didn't say this here, but they were the same mass and same radius. It's just how the mass is distributed across that radius. So the one that has less I is going to be the disc, because the hoop has a greater I because its mass is all far from the axis of rotation, its center. So then your answer is the disc, because it has less I, so it spends less energy on rotation and more on getting faster, which is why it reaches the bottom first. The hoop has greater I, so it has to spend more energy on getting it to rotate, which means that it's going to rotate slower, so therefore the velocity will be slower. It has less energy, it spends most of its energy on rotation and less on just getting faster. Right, number 15, so two balls A and B of different masses are stuck on either ends of a thin rod. A student holds the rod by both ends and lets go at the same time. Will it rotate as it falls? Why or why not? If it does rotate, what direction will the rotation be? So we should hopefully have time for the period, I'm sure I do, have showed you this in class, and you know that it will not rotate as it falls. And the reason, right, is because at first it's not rotating. If you have something that is not rotating, to cause it rotating, you need a torque. So it would need a net torque to cause a rotation. So like if somebody was like holding it and then like pushed one side up or down, doesn't matter, something that would, like a force acted perpendicular to the R, or if you held it on this side and pushed up or down, that would cause a rotation. But what's happening is that they're being held and then they're just let go. Now there are forces acting on it, in this case like the force of gravity acting on both, and they are not the same because they're different masses. B is much bigger, so they're going to have different forces of gravity. This has a much greater force of gravity than this one does, which might make you think like, oh, this is greater torque, it should rotate, counterclockwise. But remember, your torque, finish off that word, so torque is RF, and yes, B has a greater force, but we don't know what the R is. In fact, if it's not being held at a certain point, so that it has to rotate about that, it's going to just rotate around its own center of mass. So this would rotate around the center of mass. So this is different than questions like here, where I said like this is the pivot point. There's something holding it in place and it rotates around that. Or I think there was another one where I said like it pivots, or yeah, I put the fulcrum right here. So this is where the where it can rotate about. If there's nothing like holding it in place, there's no like fulcrum or like fixed point, then the thing would just rotate around its center of mass. So its center of mass is not going to be in the center because there's more mass on this side, so your center of mass is going to be closer over here. So this, I'm going to label this center of mass. I don't know exactly, but it's definitely not in the center. It's closer, it's skewed over to the bigger mass side. So yes, B has a greater force of gravity, so it has a greater force. B has a greater force, but it's closer to the axis of rotation, or like this pivot point, so it has a smaller R. So smaller R with a greater force is going to balance out this smaller, so this one has a smaller force but a bigger R. So the two are going to actually end up canceling out, so their torques are going to be balanced. So they will have balanced or equal torques, so no rotation. Not unless something starts it rotating in the first place. If you just let go, gravity is not going to rotate it on its own because it will just rotate around its own center of mass and then it's balanced, so it doesn't need to rotate. That would be different than if I was holding it in the center and then just just holding the center, let it go, and then it would start to rotate. But if there's nothing holding it in place to pivot around that, it'll just go around its own center of mass. All right, and then the last one, so let's say I take this same system. So at first I just dropped it and it fell to the ground. They hit at the same time, it didn't rotate. Now let's say I take this and I start rotating it. So, I don't know, like this would be like I drop it versus I start it rotating. You probably couldn't see that. If you have something you start it rotating and then you let it fall, I want to know with this one, while it is rotating, take more or less time or the same amount of time to hit the ground as when it was just dropped like this. And the answer is it actually takes the exact same amount of time as before. Now, there are those of you who probably said, oh, it takes less time because it's going to go slower because it's spending most of its energy on rotation. Because that's what's happening here, right? I started with just potential energy, and then it went into both kinetic and, rotational and translational kinetic energy. So the one that had the higher I took more rotation energy and less translational. But if you think about what I'm saying here is, okay, I have this one, and it just drops down. So this is going from potential energy to all kinetic energy at the bottom, all translational kinetics. It's not rotating. What I've changed here is I'm dropping it from the same height, but I already have a rotation. So I'm starting not just with gravitational, I'm also starting with rotational, right? That was there when I dropped it, so I start with the kinetic of rotational. So the bottom, yes, I do have both. It is rotating and it is getting faster as it falls down. It's accelerating down with gravity. The difference is that I also have these two terms, but when you set it equal, you're going to have UG equals KE translational, and then here UG plus the KE rotational equals KE translational plus KE rotational. And then assuming that it didn't angularly accelerate because the torques are balanced, right? It would rotate around its center of mass if it's just being dropped, even if it's rotating, because it already was started rotating. Ow! It would go around its own center of mass, so it's not going to have any net torque. So let's say I started rotating, it'll just continue at its same speed because there's no torque accelerating it. So this is the same energy, rotational energy, as it had before. So yes, it has more energy at the end, but it also started with more, so it's still getting the same amount of translational kinetic energy from the potential that this one did. So they have the same speed overall, same linear speed. This one just also is rotating, so they're going to hit at the same time. Hopefully that made sense because the visor is about to start.